Hello, I think we're ready. Welcome to these video/audio lectures. They're just screencasts, really. This is what they're going to be like. They're going to be screencasts with PDF or PowerPoint slide presentations with them. They're going to be based generally on OpenIntro second edition. And Mine Chetinkaya Rundel is one of the authors of this. And so the first few presentations I'm going to have are going to be based on her original slides. So let's just get started here. If I can remember how to get started. Okay. So the first thing we need to learn is about data. And we won't stop talking about this or stop thinking about this entire semester. And if you continue in any kind of research or statistical kind of involvement in any way in your career, you'll never stop thinking about data. You'll never stop thinking about the nature of data, what it's telling you. You have to treat different data differently. The nature of the data determines the way that you have to treat the data to get appropriate answers from it. So first, let's talk about just kind of how we organize some basic chunks of data. Now, excuse me, sorry, there's going to be a lot of coughing in this. The way we organize data frequently is in this data matrix. So you can see this square here, it's represented, or this rectangle here, recreated from your textbook. This is a data matrix. Now here, these dots, that's not part of it. In other words, this should be 50 lines long, but just so you can see the structure of things, you do 1, 2, 3, leave out everything, and then they chose to put in number 50 to show you that was the end. A data matrix holds a lot of information, and this is the standard way that we organize information when we're going to analyze it through statistics. This is the most common way to do things. Now down here, this is what you might call a code book. This is a description of the different variables, in other words, the different columns, because each column is a different type of information, and what kind of information is in each of those variables. So let's talk about some of these pieces. Each cell is an observation. Now these aren't cells, by the way, this is just numbering. Different software programs, or if you're writing things out by hand, it's often useful to number the observations from 1 through something or other. Sometimes the numbering becomes its own observation, like if it's a participant ID number or something like that. But sometimes you're just numbering the matrix so you can easily see what row you're on. So those aren't observations. But this no right here, this is an observation. It means that subject number 1 or email number 1 was not spam. By the way, this data matrix is taken from a data set that you can get in R with the OpenIntro package called Email 150, or Email 50, sorry, which has 50 emails. They just kind of took 50 emails and counted these 5 characteristics, or observed these 5 characteristics. So number 1, this observation, email number 1 was not spam. There you go. This observation over here, 28. That observation tells us that email number 3 had 28 line breaks in it. So each individual piece of data is called an observation. The cases, or sometimes you call them the subjects, or sometimes you call them the individuals, but they're not always people. As you can see, this is emails. Each of the cases is an email, not a person. That's a row. So this is email number 3. There's nothing special about number 3. Sometimes the order makes a difference and people chose them for some reason, but sometimes they didn't. Sometimes it's just how they happen to be in their data set. Sometimes that matters and sometimes that doesn't. All these things to worry about. Okay, the variables are similar observations from multiple individuals. Now, a column is a variable, a row is a case or an individual or a subject or something like that. So a variable cuts across all individuals. So there's a format recorded for each of the 50 emails. There are 50 individuals or 50 cases, 50 emails. And so for instance, we know the format of each email. So the format is a variable. It is something that can vary between individuals. Now, if you find something you think is a variable and everything has exactly the same value, sometimes that means it's not actually a variable. It's a constant, in which case we're not actually very interested in it. You probably take it out of your data. So variables we're going to think about pretty deeply a lot. Because a variable, all the observations in one variable need to be the same type of data. And so when we're talking about variables, we're talking about types of observation. Observation is this process of assigning symbols to data collection is the process of, or measurement is the process of assigning symbols to observations. So you learn something with your senses, like you read it or you see it or you hear it or something, And then based on that, you process it in your brain, and you write down or put in a computer a symbol or a set of symbols. Now, those symbols can be words or they can be numbers. Those are the most common ones, but sometimes there are other things, mostly numbers and words. Now, numerical variables are the ones that we're maybe the most used to dealing with. Numerical variables means numerical observations. Every observation or every measurement is encoded with a symbol of a number. Now, it's not the symbol that makes it numerical. You can encode anything with any symbol. You could take something that should be numbers and encode it with like little pictures of animals or words or whatever you want. The symbols are not what matters. They're just a clue to what's going on if you were a smart researcher and used the right kind of symbols. What's going on here is that underneath the symbols, this is truly numerical data. They are quantitative. That means these are quantities. There are differences of degree, meaningful differences of degree. Some things are more than whatever the variable is, and some things are less than whatever the variable is. So like a person's age can be, if you have a high number, it means that person has more years on this earth than a person who has a low number. A person who's 21 is older than a person who's 18, right? So this is a numerical variable. Quantitative variables, oops, let's go back to numeric variables, usually represented with numbers. And the differences between all the potential numbers, not just the numbers in your data set, but all numbers that could possibly happen, are mathematically regular. Doesn't mean that the symbol differences are regular, but the reality of the differences is regular. So temperature, for instance. Temperature, let's say we measure it in Celsius. Doesn't matter. All our temperature scales were designed this way. You measure temperature in Celsius. The difference between 1 degree and 10 degrees is the same as the difference between 101 degrees and 110 degrees. So in both of those situations, the difference is 9 degrees, and those 9 and an individual degree represents a regular quantity. An individual degree represents a certain amount of energy added to or taken from a system in this case. But this is quantitative. It's a truly numerical system. Now this book says numerical and categorical, but there's another system that says nominal, ordinal, interval, and ratio. And you'll note down here, numerical variables are sometimes called interval and ratio. The difference between interval and ratio, they're both numerical scales, numerical measurement types, but a ratio scale has a zero that's actually truly meaningful. So Fahrenheit is not a ratio scale. Don't focus on the interval ratio thing too much. We're not going to make a big deal out of it in this class. I'm just letting you know because you might come into this distinction elsewhere. Fahrenheit is not a ratio scale because 0 degrees Fahrenheit doesn't mean a complete absence of the thing you're measuring. Temperature is energy. So each degree is a certain amount of energy that could be in a system more than the degree before it, right? Just it's always the same amount of energy. And so Fahrenheit has always the same amount. Each degree Fahrenheit is the same size as each other degree, whether it's going from 1,000 to 1,001 degrees Fahrenheit or from -20 to -19. It's the same size of a change. It's the same change in temperature. However, 0 Fahrenheit is the freezing point of water at sea level or something like that. So that doesn't mean the complete absence of energy. Celsius is not a ratio scale either because 0 Fahrenheit is not freezing. 0 Celsius is freezing. 0 Fahrenheit is something insanely colder than freezing. I'm going to have to remember that now that I'm in a warm or in a cold place. But Kelvin, that's a ratio scale because 0 means a complete absence of energy. Anyway, I'm not going to go too much about that because we're not going to make a big deal about that, but you should know the distinction between numerical and categorical variables. So let's look at categorical, sometimes called qualitative measurement or qualitative variables or qualitative data, because we know the quality of something, but it's not meaningful to talk about differences of degree between things. So the classic example is religion or a person's sex, a person's biological sex, male, female, or other. Because biologically you can have a number of disorders that make it kind of questionable genetically which sex biologically truly you are. But there's usually only considered to be 2 values. Technically there's 3, but we usually talk about 2. But even if you assign 1 to male and 0 to female the way it's often done, that doesn't mean male is greater in sex in some way than female. It doesn't mean that. It doesn't make any sense to say that. So even though you could use numerical symbols to represent those observations of what a person's sex is, that doesn't make it a numerical scale because the actual measurements, the observations themselves are inherently, they can't tell you about degrees between the observations. I can't tell you that one observation is automatically higher on this variable or lower on this variable, has more of this variable or less of this variable. Now, I had a colleague once tell me that if you just turn that, instead of saying male, female, you say number of penises a person has, and men would have 1 and women would have 0, or you say number of vaginas and women would have 1 and men would have 0. Well, suddenly you have a ratio scale. Now it's numerical. Anytime you're counting something, it's numerical and it's ratio. But if you're saying sex, male, female, that's not counting anything. That's talking about a quality of the individual. And so that is a qualitative or a categorical measurement. You can't do math on that. Even if you assign numbers to the observations and do some math, then your results are meaningless and crazy. These are sometimes called nominal and ordinal scales. Now, ordinal is very special because an ordinal scale is not like male, female. It's like first, second, or third in a race, or strongly agree, strongly disagree, etc. The different points on the scale, the different observations that a person or a case or some value could have, yes, there's a clear greater than, less than quality to them. So if you came in second in the race, you went faster than the person who came in third, right? But there's no guarantee that the person who got second was as much faster than third place as the person who got fifth was faster than sixth place. So the gap between second and third is not guaranteed to be the same or even mathematically regular compared to the gap between like fifth and sixth or something like that. The gaps between the numbers, you can't claim that they're truly regular. So mathematical purists will say ordinal scales can never be treated with the procedures that are actually meant for numerical scales, because ordinal is technically categorical. And for most ordinal scales that's true, but there are a couple of exceptions. Number one, some ordinal scales behave so much like numerical scales that some social science researchers mostly will analyze them as if they were numerical. And the second situation, which is common in psychology, is what if you give people 30 questions and all of them have a 5-point Likert scale: strongly disagree, disagree, neither disagree or agree, agree, and strongly agree. Those 5 points that you're very used to seeing on bubble sheets and things and on computer surveys. What if instead of just analyzing one of those, you give a person 30 of those and then you take the average of those 30 things? Well, under certain conditions, if you made the scale correctly, then yeah, it makes sense to treat those as if they were interval, in other words, numerical. But we'll talk about that a little bit more. That is not an important fact for you to remember right now. Right now, just focus on qualitative measurements, categorical data. Now, within numerical data, you can talk about continuous versus discrete numerical data. Continuous numerical data is data that it makes sense to keep subdividing the points between the data infinitely, or between the points between the potential observations infinitely. So let's go to physical measurements. Any physical measurements work this way. So let's say, I don't know, miles per gallon. That's a physical measurement. What miles per gallon does your car get? I drove up here a little while ago to Fredonia, and my car got about, I think it was loaded down, it got like 30 miles to the gallon. Well, I could imagine that another car might get 29 miles to the gallon, right? Is it conceivable to imagine that a car could get 29.5 miles to the gallon? Yeah, sure. 29.75? Sure. 29.9? Sure. 29.86, 0.865, 0.86438, right? You can just keep dividing the points and the space between the points over and over and over again. There's no point at which you can't divide it anymore. You're only limited by your ability to measure. That's a continuous numerical scale. But there are also discrete numerical scales. Note the spelling, ETE. Discrete with EET, that's like sneaky or keeping it on the down low. So a discrete measurement, EET, would be like sneakily staring at somebody and estimating their height and then looking away before they look at you. That's not what we're talking about. This kind of discrete with ETE means individual chunks that cannot be split up. And this has to do with sort of logic. And it has to do with how you've defined your variables. So most of the ways that we define number of children people can have are discrete. You either have 2 children or 3 children, not 2.5. Not like, well, the young one's kind of dumb, so we just count him as half. Now that doesn't actually make any sense. Most people would say that's not the way it works. Or this one's very small, it's only a half a child. No, it's an entire child. Its size doesn't have anything to do with it, etc. There are a lot of binary systems. Anytime that you can recode something as some observation as yes or no, true or false, has it or doesn't have it, suddenly you have a discrete system, a discrete numerical system. There are a lot of examples of systems of measurement systems that are discrete, but if you redefine them slightly, they could become continuous. And so sometimes there's some fluid room to move between here, and like many things in statistics, the way you approach it depends on your assumptions and the way you choose to conceptualize things. But yeah, continuous versus discrete. So categorical variables, you can have regular, sometimes called nominal variables, and that's that they're the observations themselves and the information about the observation. The only thing, so think of things this way. You look on a sheet of paper and you see some person's written the values from a variable in a column, and you notice that one value is different from another value. How much can you infer from that? How much can you conclude from that? A nominal system, or regular unordered categorical variable, the only thing you can conclude from that particular fact is that those two observations were different. If the symbols on the paper or in the computer are different, then the observations themselves were different. So the example of religion. So if you have people as your cases, and one person's religion is listed as Catholic, another one as Buddhist, from a numerical standpoint, all you can tell between those two things from seeing that the words Catholic and Buddhist are different is that the people had different religions. Now, if you knew lots more about them, okay, but we're assuming all you know is what's on the page. You can't assume that Catholic is greater than Buddhist in religion, or Buddhist is greater than Catholic, and even if that insanity were possible, which one was how much greater? No. All you can conclude is that there is a difference. That's nominal or regular unordered categorical variables. So there's a lot of examples of this. Sex is one I mentioned, religion, a lot of demographic things like town of residence, nation, political ideology. Unless you're measuring how strongly, then suddenly you're in the world of ordinal measurement, which is next. Ordinal measurement is where there is a clear order, but it's not clear what the differences between the categories are. So just like I mentioned before, anything that has a first place, second place, third place, that's ordinal because the measurement system itself, going purely on what you would see on a piece of paper, does not tell you what the gap between first and second is, or what the gap between second and third is. Now, a true numerical system, you would automatically know what the gap between each of the symbols meant. The gap between 1 degree Celsius and 2 degrees Celsius, you know how big that gap is if you look some things up. But the difference between first place and second place, or third place and fourth place, it's not clear what that gap is. But it is clear that first place is faster than second place in a race, and second place is faster than third place. So Likert scales are the classic example of ordinal. And like I mentioned, every once in a while, in sociology especially, or political science, you might find a Likert scale that's a single Likert scale item that can validly probably be treated as numerical because it's been studied so well and it makes so much sense. Both of those things are important, by the way, not just that it makes sense, but also that there's empirical data backing this up that shows that it behaves as if it were numerical discrete. In psychology, we get around this partially by creating psychometrically valid, psychometrically sound scales made up of multiple Likert scale items, and then we average them, either by adding them together or just taking the mean. And that really makes them behave as if they were interval if you've made the scale well. So when we're talking about variables, we can look at variables one at a time, and we can say, what's the average of this variable? What's the minimum and the maximum value of this variable? Or what are all the possible values of this categorical variable? But sometimes we want to put some variables together and look at association. So this is a graph I'm sure I'll show to you before because I like it. It's from my dissertation like a decade ago. I looked at people's the strength of people's religious fundamentalism and then the strength of people's right-wing authoritarianism in this study. And you can see the red and the green dots demonstrate that the red people were undergraduates and the green people were treatment professionals, so therapists and like that. And this blue line is the line of best fit if you throw everybody into this graph. So this graph shows you each dot has a value on two variables. This is a person right here. It's an undergraduate student who was slightly lower than average, so like a -20 or something on authoritarian attitudes, but above average on fundamentalism, religious fundamentalism. So we can represent relationships between more than one variable. Sometimes the relationships aren't of all the values in each variable variety, but rather we're just looking at the means. So you've got one variable. So let's say this is decrease in symptoms, So up here is great or decrease. That means whatever the treatment is, it's doing better. So I got this from a Stack Overflow question and stole it shamelessly. Here's a decrease in symptoms, so higher means you're healthier. And you have all these different treatments, treatment A, treatment B, treatment C. So it could be something medical. I think this was just used as an example for training purposes, so I'm not sure there's any real data behind this. And these are called box plots. The middle here is an average. So that average is lower than this average. So each of the treatments gets progressively better until up here they're getting better, but not very much. So the top 3 treatments are pretty similar. The average decrease in symptoms between this and this and this is really similar. That's actually not too different. So this is something that we do. This is one variable, by the way. The y-axis is a single variable. It's the response variable, decrease in symptoms. Now let's stop there for right now, and I'm going to try and break these up into some manageable chunks and see if that'll help us make sense of them.